Hello, 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 and welcome back to Kerbal Space Programming. We are back, and we have a new vessel that we will be putting into orbit. You may notice that I have added some additional mods, which are going to make things look rather beautiful. Most of these are beautification mods, but the one that is not is these surface lights here, because the existing lights are a little bit troublesome. They tend to stick out. These seem to be relatively balanced. The output is a bit less, and they consume the same amount of charge. So I figured, hey, you know what? At the expense of leaving stock a little bit, I figured that was fair. The other thing that we have on this vessel, in addition to all of these solar panels, is this little thing. This is the Kerbal engineering system, and this will give us some flight telemetry that we can keep an eye on. Let me open up that show engineer, and don't show it over there. And we can take a look at a whole bunch of cool stuff like our vessel's delta V and thrust and mass and all kinds of crazy things. And the reason we're putting this on here is because we are going to want to calculate that stuff ourselves, and we would like to have something that we know works so that we can verify our calculations. But yes, we are going to go ahead and launch this, so let us back ourselves away from the launch pad. Oh, there we go. Okay, just come on, I can mouse. And let's see here, there we go, F2, and let us transmit our launch script. There we go. Oh, look at that. You'll also notice there's light coming from the bottom of these rockets. We're getting a significant amount of light there, and that is something that's it's also a mod. Oh man, this is really cool. Oh, and I didn't even show you, I suppose I can't right now. The actual probe core for this ship is inside this service bay, and it is surrounded by a whole bunch of batteries inside there, which is pretty cool, because this satellite is actually going to go ahead and get us up into a turbostationary orbit, and we've got a whole bunch of dishes on here, and the idea is that this is going to serve as kind of the first bit of our next foray into satellite operations, because a lot of you expressed some frustration with the existing satellite system not being as awesome as it probably could be. We put a bunch of smaller satellites up. Oh, I guess they exploded on the way down, and I guess they're actually probably going to hit the Space Center. I hope not. Okay, well, yes, you see, so I've added a whole bunch of visual mods, and we see we have some city lights and stuff. Some of them appear to be kind of over the water. I guess those would be piers, or perhaps Atlantis is somewhat nearby. I don't know, but it looks kind of cool. We've got this skybox and all this wonderful stuff. But yeah, so the reason that this video is a bit delayed is that I had a disaster with my machine, which ended up meaning, there we go, which ended up meaning that I had to basically give up on my Hackintosh and set this up as a Windows machine. And so I figured, well, as long as I had to go ahead and set up a Windows machine, why not go ahead and add all of the really pretty mods and stuff that I can get away with now, because I'm running on a machine that can take better advantage of the graphical stuffs. So yes, this craft is going to basically be our first turbostationary satellite, and what that means is that it will stay in place over Kerbin, so it will rotate around in its orbit at the same speed as Kerbin rotates, so it should be kind of directly above the Space Center at all times, and then we can use that to bounce these, bounce our satellite relay between various crafts. So our low satellites have drifted out of orbit because their orbits are slightly different from each other, and it means that we end up with kind of iffy signal, and a lot of you express frustration with that, so we're going to work on trying to address that. But the thing that we have to keep in mind is that those low satellites maybe don't have a lot of fuel left, and we honestly don't know how much fuel we will need to deorbit them. That's not something that we have gone through and done the calculations for. It is something that we could get from well, actually, no, we can calculate the amount of delta V, that is the change in velocity that we can achieve. We can determine that, and we can look at, and even Kerbal Engineer will actually give us that information, but we don't know right now what it takes to change our periapsis or apoapsis. How much change in velocity does that actually require? So throughout this episode, we're going to start building up a library of useful utilities and functions that will help us calculate these sort of things, because this is going to be important if we want to, say, go to the moon and for example, know that we have enough fuel to go to the moon and that sort of thing. But obviously we don't want to be irresponsible space pioneers and leave all these things in orbit. So we want to make sure that, these things, yes. We want to make sure that if we have to decommission these Omnisats, that they have enough fuel to do so. And actually, a fun fact is that in the real world, there is a parking orbit, or a graveyard orbit, which is what happens when you have a satellite that you cannot seem to get into. Okay, that volume is really loud for me. I'm going to turn that down a little bit. But yeah, so there is a parking orbit, a graveyard orbit, I should say, where basically if you do not have the Delta V to get yourself back into the atmosphere, so they've put up these telecom satellites or things like that, basically what they will do is they will boost them into a high enough orbit that they're reasonably sure that they are never going to decay and collide into other vessels and become a problem. But it is still, potentially an issue that if we end up with too many things in the graveyard orbit, they can collide. And okay, there we go. We are doing our circularization. And I think I'm actually going to skip talking over this launch script because it is ridiculously similar to the stuff that we've done before. I think the only thing I did was take our burnout check and actually move it into a separate file because that'll be kind of the start of one of our libraries. But there we go. We are finishing up our circularization, and there we go. Our craft is there. And of course, all of this is happening at night, which makes this a little bit difficult to see. But yes, we have two Omni antennas for redundancy. In fact, the omnidirectional antennas don't much matter because this thing is going to be up in a high enough orbit that it won't be able to connect with the space end that way once we boost it up. The big things that we're going to be looking at are, got to put up the UI. There we go. Do we have a connection? We do have a connection, so I can activate this briefly. That's a little cheaty because we should probably transmit an instruction. We see we've got these dish antennas, and then of course the dish at the very top. So I'll go ahead and deactivate that. Now the thing is that this requires a ridiculous amount of power, and that is why we have this service bay. If we zoom in here, there we go. You can see that, so there's a probe core inside there, which I don't think I can even actually get at. And then we've just got all of these batteries kind of surrounding the thing, giving us a ridiculous amount of electric charge. And then of course we had to really deck this whole thing out in solar panels and solar panels and solar panels. Okay, come on, there we go. Yes, I'm using a different mouse now, so I'm trying to remember how to actually do the panning stuff. Okay, but yeah, so we have now got this into a circular orbit, and what we want to do is boost this up to a Kerbal stationary orbit, which is 2,800 kilometers thereabouts. But of course, to do that, we want to make sure that we know exactly how much fuel that's going to need. And because this ship is equipped with the Kerbal Engineer system, we can actually use some of these values to verify our own calculations. So for example, it'd be nice to know, like here, we see that, okay, after doing our circularization, we have enough fuel to make this amount of to change our velocity by 2 kilometers a second. We want to make sure that we can actually know that inside our programs because we will use that to make decisions about whether or not we can do things. So let's jump over and start building ourselves some scripts. Actually, no, I take that back. Before I do that, let's talk real quick about what the plan is for this. So remember, we've kind of done this before when we were boosting up the Omnisats, but we want to do it better. So I'm going to go ahead and add a maneuver, and I'm just going to pick some arbitrary thing. So we did this when we were last talking about this. We talked about it in Photoshop. Let me bump that up so that it's not colliding with stuff, because this is just as an example. So we've got this, and I'm going to go, and by the way, you get these maneuvers because I have upgraded our tracking station. So now we have this, and we can see that it shows us the delta V required to make that change. And that was something that we just had to kind of cross our fingers and hope that we had enough fuel for in the past. But now we can actually say, okay, well, this is going to be 694 meters per second, and we have that and plenty to spare. And then, of course, once we get up to the top here, we'll go ahead and circularize our orbit like, what is it? Where is it circularized? Come on, circularize. That's more than circularized. Come on. Okay, I missed it somewhere. There we go. Okay, so about there. So now we can see kind of more clearly, except for all of these other orbits that are kind of getting in the way. But so when we want to do our transfer orbit, and this is called a Hohmann transfer, is that we have our elliptical orbit like this, which requires a certain amount of thrust, and then we have our circularization burn, which requires some additional amount of thrust. So if I click away here, we can see that our first burn is 700 meters per second, and then our second burn up here, we can see the maneuver, and it shows us the delta V required. What we want to be able to do is actually calculate that ourselves inside our own program so that we can determine exactly how much fuel we need, and then we can also figure out whether the Omnisats have enough fuel. You can calculate kind of that first burn as if they were, if they were going to go ahead and drop their periapsis inside the atmosphere and determine, okay, exactly how much fuel do we need to have remaining to make sure that we can get these in there. And then if we have some left over, maybe we can work on spacing those out again. So thankfully, all of this stuff already kind of exists. This is orbital mechanics math that already exists. All that we have to worry about is translating it into KOS code. So let's jump over to Wikipedia, the source of all accurate information, and take a look at the rocket equation. So this is the rocket equation, or the Tsiolkovsky rocket equation for calculating delta V for the rockets and the maneuvers. And now that I've offended all of the Russian viewers of this video series, we can move on. Okay, so yes. What this tells us, and this is some math, it's some scary math, it's not even highlightable, it's an image, that's how mathy it is that our delta V is equal to the exhaust velocity times the natural log of the original mass divided by the ending mass, so the mass once we have completed a particular burn. So what we're actually going to do is we're going to go ahead and we'll say, okay, well, we'll take the current mass of our ship, we'll divide it by the mass minus the liquid fuel and oxidizer, and take the natural log of that, and then multiply it by what our exhaust velocity is. So let's look at our equation, or look at our script rather. So our exhaust velocity is actually given by the engine's ISP, say engine ISP, and multiply that by the gravitational constant. And that is how we get what our exhaust velocity is. This is just because it's KSP. And then what we want to do is obviously multiply that by the natural log, ln, and thankfully that's a function in KOS. We'll say ship mass divided by the dry mass. Now, there is a function in KOS called ship dry mass. Unfortunately, there is a problem with this function at the moment related to bugs in KSP's API and various things that I'm not going to get into, so we'll go ahead and have to calculate that ourselves for the time being. So what we need to do now is figure out, okay, how do we calculate this dry mass and how do we actually get this engine? So what we're going to do is we're going to assume that we're running on a single engine. What we can do is say list engines in ship engines. And then we've got this ship engines variable that holds all of our engines. And so instead of saying engine here, we'll say ship engines 0. So we'll just get the first one in that list and take the ISP of that. Now we need to calculate the dry mass. And so what we want to do is we want to say set dry mass to something. Well, it's going to be ship mass, right? And then we have to subtract whatever the weight of the propellants are. Now, how do we calculate that? Well, we can say ship liquid fuel. We can get all of the total of our liquid fuel, and we can say plus ship oxidizer. And that's going to give us the total of that, right? But that's only going to give us the number of fuel that we have, that you see in the resource tab. What we need to know is the actual mass of that. And it just so happens that this is equal to 0.005 tons, which is the metric that we're using for ship mass and all this other stuff. It doesn't necessarily matter, remember, what these units are, because we're only calculating them relative to each other. So if we were calculating, we go from 5 grams to 2 grams or from 5 tons to 7 tons, it doesn't matter. We just need to make sure that those units are the same. So let's wrap these inside parentheses, because we want to take the total of all of our liquid fuel and the total of all of our oxidizer, and we're going to assume that we're going to burn all of it. So we're making a bunch of assumptions here. We're assuming that we're using a single engine and that we're using all of the ship's liquid fuel and oxidizer in that burn. Let's go ahead and add that into, put that in here, minus this, and we'll, there we go. And yeah, we'll put parentheses around here. It's not strictly needed because order of operations will make sure that this multiplies, but you know, let's just keep it clean. So we've got that. So now we have our dry mass, which is equal to what the mass is currently, minus the weight of all of the fuel that we'll be expending. And there we go. Now we have our formula to get us our delta V. You notice I've also named these functions, I've given them a little bit of a prefix just to kind of make sure that we know where we're eventually going to put these, because we'll eventually want to put these up into separate libraries. I'm going to call this TLM for telemetry. This is just giving us information. And these next two scripts are MNV for maneuver, because they're about maneuvers. So this should hopefully give us our delta V, and what we'll want to do is actually upload this test script and have it run against our current vessel and see, well, okay, does Kerbal engineer agree? Do the maneuver nodes agree? And that sort of stuff. So next, let's take a look at maneuver time. Because we take some time to actually complete a thing, let's go ahead and say, so we want to operate on a particular delta V requirement. So I want to say, if I need to, if I need to change my velocity by a certain amount, then how long is it going to take me to do that? Well, we can calculate our maximum acceleration by taking what our maximum available thrust is and then just dividing it by the ship's mass. So we'll say ship max thrust divided by ship mass. That's our maximum acceleration, which is great. And then we'll just say, okay, so that's the amount of velocity that we can change in a second. Let's go ahead and return that, the delta V divided by the maximum acceleration. So we're saying, here's the total velocity that we want to change, and here's how much we can do per second. So that's going to leave us with a certain number of seconds. And hopefully, we'll again compare this to the maneuver notes that we get from the tracking station and see, does it roughly match up? Now, this last one is going to be tricky. We're going to have to jump over to Wikipedia again to figure out how we calculate Hohmann Transfer delta V. Okay, so here we have some stuff for the Hohmann Transfer orbit, and we see, look, it looks pretty similar to what we had plotted out with our maneuver notes. We have this first delta V burn, and then we have this second delta V burn that gets us into our higher orbit. Yay, yay, yay. Okay, give us the math. Give us the math. This looks confusing. Okay, solving for this gives us more confusing stuff. Okay, here we go. Here's the math that we have to implement, and this is scary. This is big. This is terrifying, but it's okay. We will be just fine. So this first one is going to give us the delta V requirements for our first burn, and the second one's going to give us the delta V requirements for our second burn, and then obviously the total delta V requirements is going to be the sum of those two. So let's jump over. Well, first off, let's take a look at what these values are. So we've got a mu, we've got R2 and R1. And it looks like those are the three values that we actually have. So we can try and figure those out. So U, it says, is the standard gravitational parameter of the primary body. And actually, it turns out that we get that from KOS. So that'll be okay. R1 is the distance of the orbiting, or R is the distance. Okay, so we're going to take the radius at our start, that's going to be R1, and the radius at the end, that's going to be R2. And because we're not in a completely perfect orbit, we're going to take the semi-major axis, which is the average between our apoapsis and our periapsis, the highest part and the lowest part of our orbit. So let's jump over and see if we can start trying to script this. Okay, so if we try to jump in and just write this out right away, it's going to be a little bit scary. So let's start off taking our first delta V, right? So we'll say V1. Now, we know that first part, that first half of the equation is the square root of mu, and let's just call it u, right? We'll say the square root of u divided by R1, right? Okay, that one's easy enough. So that one we can just leave there, and let's add some space so that we don't have to worry about it and don't accidentally screw it up. And then we're going to multiply that by that second term, and that second term is much more confusing. So let's go ahead and say square root, and then we'll add a whole bunch of space here. We'll say, okay, so we've got that first term, which is 2 times R2, and over. Remember, this is not valid code, but it's okay because we're going to clean this up later. We just want to make sure that we can see what it is that we're doing. We'll say and this is R1 plus R2. And that suddenly doesn't look quite as bad. And then the last thing is that -1 here. And then this whole thing is in parentheses because this first term gets multiplied by that with parentheses. So, okay, we've translated that scary looking math formula into pseudocode, which means not really code, but sort of code E. Let's go ahead and actually try and clean this up just a little bit. So I'm going to put parentheses around here and around here, and I'm going to turn this into a slash. And let's go ahead and clean this up just a little bit. We'll just remove a bunch of these spaces. Okay, so we've got that. -1. Oops. There we go. Clean this up. And there we go. Now we've removed all these spaces, and now we should have set v1 to this. And we can even, if you're using depending on your editor, if you're using something that's designed for code, you may actually get these parenthesis highlighting to make sure that we're actually closing the stuff we should be. So now we have our formula for v1, and this would be very difficult for us to write out ourselves initially, but it's okay because we set this up in a much simpler way and then kind of collapsed it. So let's look at v2. Okay, so this one is very similar. See, u divided by r2 instead of r1, and then square root of, oops, nope, not square root yet. Let's actually put these parentheses in first, right? Say 1 minus, and now square root of something. And we'll say, so the first term is 2 times r1, and that's divided by r1 plus r2. Okay, so we've got that. I've added these parentheses in kind of ahead of time. So let's go ahead and we'll replace this with a slash for divide and start to clean this thing up. Put all these parentheses back where they go. 1 minus that. See, okay, so that clears itself up. Get rid of this. Go here. And we'll say, whoops. Set v2 to this. And see, all of these trailing parentheses, this would be really hard for us to do if we were just trying to figure it out on our own. So now what we want to be able to do is actually return both of these values. So I'm going to say return a list of v1 and v2. And that's wonderful. So we've got v1 and v2, we've got the formulas to do that. We're almost there, right? So there's a problem, and that is that we don't have this u or this r1 or this r2 value yet. So we need to figure out how we actually get those. Now the radius comes from the center of the body that we're orbiting, not just the altitude. Because remember, when we're 100 kilometers above the surface, we're actually significantly higher above the center of Kerbal. So what we're going to do is we're going to say, okay, you're going to pass in a desired altitude, not a desired radius. We're going to actually need to calculate that radius. So that's your desired altitude. So we can say set R2 to desired altitude plus the radius of whatever we're orbiting. So ship, orbit, body, radius. There we go. Okay. So that's our R2 value. We need to figure out what our R1 value is. And this one's a bit easier because the semi-major axis we can just get directly, and this is actually going to be the altitude above the center of the body. So we'll go ahead and say ship, orbit, semi-major axis. Remember, this is the average of our apoapsis, the highest part of our orbit, and our periapsis, the lowest part of our orbit, but it's also adding in the body radius automatically. And the last thing we need to do is figure out the gravitational parameter of the body. So this is the gravitational constant times the mass of whatever it is that we're orbiting. So the one value is what is gravity? And then the mass is, well, how much gravity? So we'll say set u to ship, orbit, body, the thing that we're orbiting, and we can actually get this directly. So we'll say mu, and there we go. We have a function that will now give us the delta V requirements for both parts of our maneuver if we wanted to transfer to a different orbit. So last thing that we're going to do is jump down and write some quick tests to see how we're doing that. So let's go ahead and say print testing functions, and we'll say print ships delta V plus TLM delta V. And this one doesn't require any parameters. We're just trying to figure out how much delta V does the ship currently have. Now we'll say print maneuver time. Let's say time for 100 meter per second maneuver plus maneuver time. We'll say 100. We'll pass that in. So that's the delta V that we want to test for. We want to say how long will it take us to complete a 100 meter per second maneuver, and then we can go ahead and create a maneuver node in our orbit and see, well, does it match up? We won't execute it, but we'll just use it to test. Then we'll say, okay, let's say print transfer. Let's see, transfer delta V to. And let's make it 400 kilometers. So if we were going to transfer to a 400 kilometer orbit, then how much delta V would it require for both of those steps? So we'll say maneuver, Hohmann DV, and we'll pass it in that 400 kilometer value. And then we can go ahead and verify, whoops, there we go. We'll go ahead and verify both of these values against what we actually get from the map view and see if they're roughly accurate. You know, they're not going to be completely the same because there'll be some, minor differences, but if as long as they're relatively similar, we can be confident that these functions are going to be helpful for us. So last thing we're going to do is I'm going to say wait, and let's say wait, I don't know, 500. So just so that it doesn't clear the screen, so we can actually look at these values and compare them. So let's jump over and see how we did. And yes, one small little error in our delta V function. We're not actually returning anything. We're just stating what the formula is. Let's actually return that. Oh man, there we go. I can type. Oh boy. Alrighty. There we go. And let's jump back and try her again. And there we go. Okay, so we've got delta V. It says that we have 288. Hey, look at that. That happens to match up with what we got from the flight engineer. I think that's good for us. It says that it will take 7.19 seconds for us to complete a 100 meter per second maneuver, and that the delta V to transfer to 400 kilometers will be 210 and then 190. So let's verify that using the map. Let's go to the map. Let's first off, we'll set a maneuver that is 100 meters per second of delta V, right? So we can see that down here. Right now it's saying, nothing. And as soon as we start to boot this up, oops, there you go. All right. Get this up to 100-ish. And okay, now we're not going to get an estimated burn because the engine hasn't fired. So what I'm going to do, and this is going to cheat a little bit, but I think it's okay. We're just going to throttle up the engine very, very briefly and cut it off right away. There we go. All right, so we get an estimated burn time of 7 seconds. That matches up with what our calculation was. So I think we can call this second function a success. Now the question is whether our Hohmann transfer calculations are also correct. So let's go ahead and set up a new maneuver. Here, let's make it a periapsis. And we're going to boost this up to 400 kilometers. I'm not quite sure where that is. We'll have to, okay, overshot it. Let's bring this down. 488, okay. 366. Okay, so we're closing in on it. Close, really close. 402. All right, we'll call that good enough, and then we'll add a maneuver for circularizing it. Just drag this up. Oh, there we go. I think that's all right. So that's getting close. So roughly about there. We're not going to be exact about it. And actually, because we can see that these things flip, because as soon as we push our orbit higher, well, then this isn't the apoapsis anymore. So let's close out of that, and let's take a look at what our predicted values were. So the first one it gave us was 210, and this one says it's 205 for that maneuver. I think that is close enough for our purposes. And it says that our circularization would be 190. Let's go ahead and hover over. And it says 194. So I am going to go ahead and say that we have a working script that will calculate the energy needed to perform this sort of maneuver, which means that we can eventually take a look at the Omnisat and various stuff like that. In fact, let's jump over to one of the Omnisats that has a connection right now, and we'll go ahead and run the script. Okay, so I've cheated a little bit. I went through and just tweaked our transfer delta V test to actually check for 60 kilometers, which is lower than we are currently in. And we see our current ship's delta V is 676 meters per second, so that's the amount of velocity we can change. It will take us 1.8 seconds to complete a 100 millisecond maneuver, and to transfer to 60 kilometers, which is enough that our orbit would decay. We only need to complete the first half of this orbit, because then we can let the atmosphere drag us down for the rest of it. But it says negative 358. So of course that's because we're burning in the opposite direction. So if we take the magnitude of that, that means that we have to save 360-ish meters per second to eventually deorbit this from its current orbit, which means that we have a fair amount of room to play with. So we can go ahead and look at spacing out these really troublesome Omni satellites in the next episode, and I will see you then. Cheers.